Hi, this is Max Gravett at Digital Scarcity. I wanted to explain a little bit about how I've solved a problem that I've had with transactions, micro transfers, token transfers in EOS. What I found, I had a project that I was working on where I had to do a large number of micro transactions. They were transactions based off of some other event that transferred revenue into the account, and then it had to respond by performing a large number of transfers. And what I found when I tried to put this all into a single EOS action, I had a problem with the number of transfers. I found that I could only do about 25 transfers in a given action. Now that varied a little bit based off of a lot of other parameters, and I'm sure it would vary based off of which network I was using. But the issue I had, it was far fewer than what I needed to do. So for the solution, what I did, and I'll walk you through this in just a moment, I created a smart contract that could handle a queue of transfers. And then it would churn through the transfers with a self-spawning deferred action. So let me jump into the design of this a little bit. So I created two tables, one for the pending transfers and one for the completed transfers. I would initially add records to the pending transfers, and we'll demo this in just a second. Adding transfers to pending, I would pass in the token contract from to the quantity to be transferred, along with the memo that we would use, and also create a timestamp just for administrative purposes. So I would add into that table as I needed to. And then at the time of my choosing, I would call in process queue. What that would do is it would read the first transfer from the table. It would execute that transfer on that token contract. It would then archive the transfer over into the completed transfers table, and it would kick off a deferred action. That deferred action would be to process another transfer in the queue, and that guy would read from the queue, execute the transfer, archive the transfer, and then kick off another deferred action for a transfer. And these would just continue until the pending transfers table was empty. So it really allowed me to write the records to the table, to the pending transfer table, to queue them up as I needed to, and then whenever I wanted to, be able to call process queue, and it could transfer. Really, it would only be limited to the amount of CPU that was staked and the time of how frequently these deferred actions would be called. So that's a quick overview. Let's take a look at the code. I'll first talk about the data structures, and then we'll jump into the implementation. So really simple, pending transfers and completed transfers. And to be honest with you, in production, I would probably not archive the completed transfers because they would be kept, on chain. There'd be a record of them just in the log, so I wouldn't really need to archive those as part of it, but just for testing purposes, I included it in this smart contract. So the pending transfer, again, it has the same records or the same attributes that I showed on the design, and there are just these four actions. One is to populate the queue. I'll show you that in just a moment, but that just creates records that need to be transferred. This add to queue is just to add a single transfer. This is essentially populate queue just calls add to queue for a number of times, just as a convenience method to add some work in there that needs to be done. Then process queue is called with no parameters, and that guy would then, call process transfer with the unique transfer ID that needed to occur. All right, so let me jump into the code. Really straightforward. Let me jump down here to the process queue. So this is, once everything's queued up, how do you process the queue starting at the top and churning through all of it. So it opens up the pending transfer table, just grabs the first item out of there, is the transfer ID, and then it creates a deferred transaction with the appropriate parameters, which really this parameter is just the process transfer key here. And another parameter here that I've hard coded in here is the delay. So this kicks off the deferred action 1 second after it's created. Let's see. Okay, so then process transfer, it just grabs the payload, which is the transfer ID. It opens up the table to find that transfer ID. Prints out a little convenience log. Then it creates the action. This is an inline action that will actually handle the transfer. So that handles the transfer as an inline action. Then it writes it to the completed transfer table, which again, that probably shouldn't be in there in production. And then what it does is it increments the iterator to the next transfer, checks that it makes sure that it's not at the end of the table. Then it will create a new deferred action to handle the next transfer, and it will put this again at a delay of 1 second. And then it will go back to the pending transfer and erase that record so that it's no longer there, and it would show in the completed transfer table. So just a couple other, in production, in the real world environment, you probably wouldn't need this populate queue method, and this add to queue may be even different. You would have some other business logic that needed to process a bunch of payments, and that would be what adds to the queue. Super straightforward, just opens up the pending transfer table and writes the appropriate parameters. And then the populate queue method, just a convenience method for testing. What it does is it just calls add to queue for X number of times. So you could, populate 50 at a time. Okay, well that's the implementation. So let's take a look. Let's test it out. Let's see here. Okay, first thing I'll do is just get my environment up. I use Docker. This is running 1.2.5. All right, and I'll link to the code in the comments below. So I have my commands here that will just kind of be our cheat sheet. So the first thing I'm going to do is just create a bunch of accounts. To unlock my wallet first. This next step, I'm going to compile the transfer queue class or a contract, create the ABI, and then set that transfer queue contract to the transfer queue account. This is just deploying the contract. Got some warnings there about the Ricardian contract. I seem to get those every time because I've never actually written one of those. I'm also going to go ahead and transfer the token. Just the default EOS IO.token. So this next step is to update the authority. Because I'm issuing transfers that need to be performed by the smart contract, I have to give the smart contract the permission to transfer on behalf of the from addresses. So here I created 3 from addresses, and I need to delegate the active permission. Let me just show you over here. It's a long command, but it's very useful. Here's the actor. So it's granting permission from the from one account to the EOS IO. Transferring to the EOS IO.code permission of the transfer queue account. And that has to be granted the permission from the from one account. So this would be in a production environment if you were transferring from some reserve account or some account where you stored all of your tokens, or the revenue account where you were collecting the funds. You would be sending from that account, and then the transfer queue would be a secondary contract. You would need to grant permission from your revenue collection account to your transfer queue account. So let's run this. All right. Now I'm going to go ahead and create the token and issue the token to a series of from accounts. I mentioned if this was a revenue collector account, you probably just have one account, but I'm going to go ahead and issue to 3 just for testing purposes. Okay. Now what I'm going to, let me show you the pending transfer. Let's see, the table, didn't need the name of the table. So there's no pending transfers at the moment. What I'll do is we're going to go ahead and create, populate the queue with a bunch of transfers that it needs to perform. And what I'm going to do, the token contract is this EOSIO.token account that I created. It's going to be transferring from 2 to 2, just 2 units of the max token. Using this memo, and this is the count, so 50. It's gonna add 50 records to the pending transfer table. Okay, so that was fast there. Okay, so here are the first 10 transfers. Just because the default for get table only shows you the first 10. Here it's the same transfer, just repeated over and over with different ID that just is an increment. And it says more equals true. That's because there's 40 other transfers that it did not print out. So what I'm going to do next is just churn through, it's called process queue. And this is where the magic happens, where it actually performs the transfers. Okay, so now that's kicked off. Let's go over and look at the log. And here you go. It's just processing through these transfers. The first part here that you see is the actual transfer. Let me pause it here. So this first one is the transfer, and then it prints out again. If you remember from the code, it prints out the parameters of the deferred transaction. So the action saying I'm performing this transfer, and then I'm kicking off the next one. You can see this is transfer ID 15 and then to 16. And like I said, it's transferring, it's kicking off the deferred action for 1 second later. What I'd love to see, I haven't figured out how to do. If you figure this out, I'd love to learn. Is read from the available CPU of the transfer queue account, and somehow make some intelligent decisions about don't transfer if you are if your CPU usage is above 80% of your available capacity. Some type of math that could determine that, look, if you don't have the CPU power to do it, obviously if you don't have the CPU power, it would just fail. But let's say that you were just close. You only want to run this when you have a significant amount of CPU available, and then you would just want to process the transfers until you were some small amount, 20%, I'm making that up, amount of CPU remaining. That would make this thing much more intelligent. Would love to figure that out. So let's go back and look at the pending transfers. Now we can look at the we're processing to 2.2. And we've got 102 MAX because it processed 51 transfers at 2 MAX each. Now, one other thing I wanted to talk about is the question of, well, if you can't handle a ton of transfers in one action, how can you handle a bunch of writes to the pending transfer table? You're going to run into the exact same constraint there. If you have 1,000 transfers to manage, you're not going to be able to write those 1,000 records to the transfer table within the same action. And you're right. So there are, what I ran into, here I'll show you what I ran into. When I was processing it, let me blow this up just a little bit. Is I could get about 100. So when I tried to populate the queue and I would pass in 100, about half, maybe 2/3 of the time it would work, and then sometimes it would error out. Transaction took too long. So I experimented with this to see where that sweet spot was, and honestly it was right at 100 records. So here you can see I tried 110, and I tried that about 10 times, and transaction took too long. And then I was at 100, and that worked. And you can see here it's right at that 29,000 of usage. I think the cutoff is 30,000, so it just barely squeaked in. And then when I jumped up to 105, too long. So that tells me that if you're not doing anything except for writing to the pending transfer table, you can write about 100 records. So you can process about 25 records transfers within one transaction. So that gives you about a 4-to-1 ratio. But I think the real use case would be if you had to queue up a bunch of transfers, say throughout the month, but then you only wanted to actually pay them, on the first of the month, or you had sort of scheduled dividends or scheduled payments, but you want to, write all of those records in advance. Now there may be a better way to do that part, but this was just a problem that I ran into while I was doing some microtransactions. This is Max Scravitt at Digital Scarcity. I hoped it helped.